All right, welcome back. Today we are just going to be looking at our other gas law, so Charles' law, and then combining the one we just did the other day, so Boyle's law, and combine Charles' law together to create something called the combined gas law. What we have right here with Charles' law, we are going to be dealing with temperature. First of all, what temperature is, or what we are going to define it as, is just the measure of the average kinetic energy of the molecules in a sample. So this is how they came up with the whole idea of absolute zero. So it's the point where there is absolutely no kinetic energy whatsoever. So of course scientists were able to kind of plot the data and extrapolate it, and they managed to get it down to the value for absolute zero is negative 273 degrees Celsius. Now, of course, for our calculations, we can't really have negative values inside of a temperature, so we are going to be using a different scale. So we're going to use the absolute temperature scale, which is known as the Kelvin scale, and of course, it goes down to when you're at absolute zero, it's 0 degrees Kelvin. So because we know this relationship between degrees Celsius and Kelvin, when we are converting from Celsius to degrees Kelvin, all we need to do is add 273, and then of course if we go from Kelvin to degrees Celsius, we subtract 273. Alright, so for example, at STP conditions, we know it's 0 degrees Celsius. So if we add 273 now, and the back of periodic tables is 273.15, you can leave out that 0.15 if you want to, and that's a little note down here for convenience, we drop the 0.15. So 0 plus 273, so at 0 degrees Celsius, that is actually 273, and if you want to leave out the 0.15 Kelvin, you can. And same thing at SATP, so that's defined as 25 degrees Celsius. So in order to figure out the degrees in Kelvin there, we just add our 273 again to get 298.15, or just 298 Kelvin. All right. So when we're going to degrees Celsius to Kelvin, that's supposed to be a K, not a C. We add 273, and when we go from Kelvin to degrees Celsius, we subtract 273. All right, so that's just kind of keep in mind there. So now that we have that out of the way, we can look at our temperature and volume relationship, which is something called Charles' law. So Charles' law states that as the temperature of a gas increases, the volume of the gas increases proportionally as well, provided that the pressure and the amount of gas remain constant. So what we have right here is temperature and volume are directly proportional. So what that means is if one goes up, the other one goes up as well. So our equation for Charles' law looks a little something like this. So you got V1 over T1 equals V2 over T2, where the temperature needs to be in Kelvins. So it has to be in Kelvins in order for this to work. All right. So let's look at our first example. So we have the initial volume of gas in cylinder is 0.30 liters at 25 degrees Celsius. What will be the final volume when the temperature is at 315 degrees Celsius? So just like before, you want to make sure you get in a habit of writing down all of your variables. So we know the initial volume, so we have V1 is equal to 0.30 liters, and T1 is equal to 25 degrees Celsius. Now it's a good habit because we know that we are going to have to add 273 Kelvin to get T1 of being 298 Kelvin, because we don't use degrees Celsius. Now we know V2 is equal to, well, we don't know, and T2 is equal to 315 degrees Celsius, and just like before, we want to right away add our 273 Kelvin to get our new T2, which in this case right here, it's 588 Kelvin. All right, so these are all of our variables. So just kind of write that down. So we're going to write our equation, rearrange, and solve. So our equation, our new one that we have right here. So V1 over T1 is equal to V2 over T2. Now just remember, when we're rearranging our equations, we have to do the operation of opposites, which means that we have to do the opposite thing to the variable in order to isolate it. So the opposite operation. Okay. So for example, we are solving for V2. So we want to solve for V2 right here. That means we have to get rid of T2. Now we'll notice that V2 is being divided by T2. So because they're being divided, in order to get rid of T2, we have to multiply both sides by T2. And this will cancel out T2 on the right hand side. So we're left with our new equation of V2 is equal to, in this case here, we got V1 over T1 times T2. So we can plug in our variables if we want. So we got V1 of 0.30 liters. T2, now just be very careful, so this is why we make sure to write out all of our variables, over T1, 298 Kelvin, and we're left with V2 is equal to 0.59 liters. And then of course our answer is 2 significant digits. Right, so remember our checklist, units and significant digits, because what we have right here, we will notice that we have the one guiding our significant digits is of course this number right here. So we got 2 significant digits coming from 0.31. So we have 2 significant digits. That works out. Now, of course, our checklist, our units, we can see liters. So we have our units, and of course, significant digits, they also check out. So this right here is our final answer. All right, so next there are a few other examples here where we have 2 more of just using them. So what I want you to do right now, pause the video and try them out. And I'm going to put up the answers very shortly. So I'm going to go through example 2 with you guys again, and then example 3 I'm just going to put up the answer. All right. So anyway, pause the video and try them. And here are the answers. All right. So writing out all of the variables, what we have right here, you can read through, but we start off with, we have V1 is equal to 25.0 liters. Now our gas, our original temperature T1 is 20.0 degrees Celsius. So remember, we have to add our 273, and we have our new temperature of 293 Kelvin. We have our V2 is equal to, we don't know, and our T2 is equal to 40.0 degrees Celsius. Now, same thing as before, we're going to have to add our 273 right away to get our temperature of 313 Kelvin. All right. Now, actually in this right here, we are solving for V2, so I'm not going to show the rearranging of the equation again just because we had it on the previous page. So if you want to go back, just kind of rewatch the first little bit and see how I rearranged that one. But anyway, from the rearrange on our previous question, we have V2 is equal to V1 times T2 all over T1. So in this case right here, we have our V1, which was 25.0 liters. T2 is 313 Kelvin all over our 293 Kelvin. So V2. Now, if you want to pay attention to your dimensional analysis and how the units cancel out, well, notice we have Kelvin in the numerator, Kelvin in the denominator, so those units cancel out. The unit that we're left with is going to be whatever, liters, and of course when we solve, we get 27 liters, 0.0 liters. So we got 3 significant digits. So our final answer, same thing. Did we get the units? Yes. Did we get the number of significant digits? Also, yes. So this is our final answer. All right. Now for this last one, I want you to pause it and of course try this one on your own. But what you should get when we're done, because now we're solving for temperature, so this one here is a little different. So I am going to go over this one, so I'm not going to write it the variables on side. I just want to go over how to rearrange something like this. So we have V1 over T1 is equal to V2 over T2. Now our first problem right here is we're solving for T2 because they're asking for what is T2, but we notice in the denominator. So of course one of the problems that of course if we just divide, because we'll need to divide by V2 to cancel out V2 on this side, we're left with our unknown variable in the denominator, which for algebra that's not how we're going to do things. So there's different ways that you can go about do this, but I like taking the reciprocal, and that is with fractions. If you take the reciprocal, or basically flip our equation, what we're left with is T1 over V1 is equal to T2 over V2. Now for in algebra wise, and of course with fractions we're able to do this because whatever you do to one side you can do to the other. So if we flip them or take the reciprocal, we're going to be left with this equation right now. So T1 over V1 equals T2 over V2. Now we'll notice that if we want to solve for this right here, we can, because now we can divide both sides by V2 to get our new equation of T2 is equal to V2 T1 all over V1. And that was our new equation. Then of course when we do solve that, what you are going to get is your answers. So once again, try these out, the equations are here, but you're going to get your temperature is equal to, we have right here, so negative 86.5 Kelvin. Okay, so of course this one here, when you do solve for T2, you are going to get degrees Celsius first, and then you subtract 273 to get your degrees Kelvin. All right, so definitely try this one. Of course, if you're not sure or have trouble with it later, just once again fire me off a little email. I could do up a quick little video of actually rearranging this again and solving it and showing you the answer and send it to you. So basically, well, after Charles' law right here, what we have next is just the combined gas law. So this is combining both Boyle's and Charles' law together for any amount of fixed number of gas, and this is the relationship between pressure, volume, and temperature. So in our equation is P1 V1 over T1 equals P2 V2 over T2. So you can notice just the P1 V1 equals P2 V2, like just the numerator portion of this looks like Boyle's law. And then of course if you cover up the pressure units, we got V1 over T1 equals V2 over T2, and that's our Charles' law. So it is a combination of both these here. So now when you are reading these questions, if something is held constant, omit it from the equation. And the reason for that, if like P1 and P2 are the exact same, they're just going to cancel out. So this is how you kind of know that if you're reading a question that says that temperature is held constant or pressure is held constant, just omit it from our combined gas law. So let's look at actually using this inside of equations. We'll look at our first example. So we have a combined gas law example where we got at 25 degrees Celsius in 1 atmosphere, a gas occupies a volume of 600 milliliters. So it will be its pressure when the temperature is decreased to 10 degrees Celsius and the volume is increased to 640 milliliters. So we have a bunch of stuff going on here. So of course, just like before, make sure to write out all of our units. So T1 is equal to, now I'm not going to show the conversion right now of getting it into Kelvin, all right, but we have 25 degrees Celsius, and this is going to equal, what is it going to equal? It is going to equal 298 Kelvin. We got P1 is equal to 1.00 atmospheres, and V1 is equal to 600.0 milliliters. We have T2 is equal to 10 degrees Celsius, or 283 Kelvin. We have P2 is equal to, we don't know, and V2 is equal to 640.0 milliliters. All right, that is everything we have. And of course, once we go from here, we have our equation. P1 V1 over T1 is equal to P2 V2 all over T2. Now, just like before, is just because we have more variables in here, how we actually solve, so the algebra steps that we use, we're still going to use the order of opposites, or the operation of opposites, whichever it was called. So that means we just have to scan really quick, highlight the thing that we are trying to solve for. In this case right here, we want to isolate for P2 for our question. What is going to be the new pressure? So we have to get rid of both V2 and T2, and I'm going to do this in one step. So we can tell that V2 is multiplied because they're both in a numerator. So in order to get rid of V2, I need to divide it, okay? So another way how this looks like, we're going to use fractions. We can just put that in the denominator because that also means divide by. Now we can tell that T2 right here is in the denominator, so we're dividing P2 by T2. So in order to get rid of it, we multiply or stick that up in the numerator. And whatever we do to the one side, we do to the other. So this way our T's cancel out, our V's cancel out, and our equation we have is P2 is equal to P1 V1 T2 all over T1 V2. So there's a lot of variables going on here, but that's perfectly okay. We just have to make sure we plug everything into our calculator and solve when we actually get going. So our pressure, 1.00 atmospheres, V1 is 600.0 milliliters, T1 298 Kelvin. Or sorry, that's supposed to be T2. So that's why you should always read very carefully so you don't make that mistake. So T2 is 283 Kelvin. We have T1, that's our 298 Kelvin. And finally, V2, which is 640.0 milliliters. And P2 is equal to. Now, of course, you should use dimension analysis always, just to kind of make sure that the units cancel out where we need. So we can see Kelvin right here in the denominator and Kelvin right here in the numerator. So our temperature units will cancel out. We also see our volume units. We have milliliters in the numerator and in the denominator, so the milliliters are going to cancel out, and we can tell that the unit that we want is a pressure unit. Atmospheres is going to be left at the bottom, which is awesome. Now, of course, when we put all this into our calculator, you have to be very careful at putting this in. And as you're going through here, you should probably have your calculators out, put this in, just to make sure you get this answer. 0.890 atmospheres. So always double check. Units and significant digits. Right, our little checklist just to make sure we have our right answer expressed the way it should be expressed. So units, we can see atmospheres and pressure units atmospheres. So a little check mark right there. And our significant digits, we read through our questioning and we got 3 significant digits here, 3 significant digits, 4, 3, and 4. So obviously answer needs to be in 3 significant digits, which we have right here. So this is indeed our final answer. All right, now the last example here. Yeah, this is the last example. So please pause the video and see if you get the correct answer. And of course, if you're still not sure how to do it, I'm going to go over it just like before. So the answer you should be getting, V2 is equal to 0.627 liters. So this should be the answer you get for that one. Of course, if you want me to go over it, once again, just kind of drop me an email and I can do up another video and just showing you how to do it. If not, we can save this for the Twitch streaming that we'll have later on this week. Once again, look at Google Classroom and see when that will be posted. All right. So, of course, complete the worksheets on gas law, or now you can actually try the section in your CYU book. And that is it for this week. All right, awesome. See you guys later.